Hello all, welcome to the second chapter of Unit 2. In this chapter, we would look into detail about the DC response of, an inverter. We'd look at the noise margins, which I have been talking about in the last chapter as well. We look at the transient response, the delay estimation, and we look a bit into logical effort. The major part of the logical effort will be in the next chapter, in the continuing chapter. This is more like this chapter is very much like the analysis we do for the RC circuit, for the usual RC circuits. We calculate the DC response, we calculate the transient response, we look at how does the output current rises and falls, how much time does that take. So, okay, this is the review of the concept we have studied earlier. So just review in your mind and try to answer these questions. What happens when the width of a transistor increases? What happens to the current? Will it increase or decrease or will not change? What happens to the length? If the length is increased, what happens in case of a supply voltage? Let's look at each of these answers. So if we review the equation of the current depends on the W by L ratio. So if the width of the transistor increases, the current will increase because current is directly proportional to W. If the length of the transistor increases, the current will decrease because it is inversely proportional to length. If the supply voltage increases, it's very straightforward. The maximum current will increase because it's again proportional to V or the square of V of the alpha, e raised to power alpha, whatever. Again, if the width is increased, the gate cap depends on the area. So both in case of both 4 and 5, if the width increases or the length increases, in both the cases the gate capacitance will increase. If the supply voltage increases, the gate capacitance will be unchanged because obviously the capacitance does not depend on the voltage. It's characteristic of the perimeter and the area and the permittivity of the gate dielectric material. So the capacitance does not depend on the voltage. I hope we remember the equation. We will see the equation in detail in this chapter also. So for DC response, we see how does V out. So now V out is the output voltage, V in is the input voltage. For inverter, let's see that what is DC response. DC response is simply what happens to V out when V in is either static 0 or static 1. It's very simple. When V in 0, V out is VDD. If V in is VDD, V out is 0. This is the functionality of an inverter. Interesting part is what happens in between. What happens when V in is switching? How fast or how slow does the V out switch? And what does that switching the speed at which it the most important thing is how fast does V out, how fast the change on V in gets reflected onto V out. That is called the delay part. That is actually the delay of a gate. A delay of a gate is very important in determining the performance of the circuit which we are designing. Now V out depends on obviously the current. The more the current or the better the rise in current, the faster V out will go to VDD or V. It depends on the transistor size. We saw in the slide earlier that the current depends on W by L and few more factors. Now we will try to solve this equation. So by the Kirchhoff current law, simple that the IDSN should be equal to IDST. So at the node V out, since both are in the same direction, we say that IDSN is equal to absolute of IDST. This way we could solve the equation, that is we keep on one side we keep the equation of for the current of the PMOS, on the other side we keep the equation of the current of NMOS. It's not a simple linear equation, so, but it can be solved. But we'll look at the graphical solution, which gives more insight into what happens during the switching. So let's now we'll try to answer the question as to what regions we saw that each of the transistors in MOS and PMOS, they operate in one of the three regions: cutoff, linear, or saturation. So we will see what happens to what regions do the NMOS and PMOS operate in during the switching and during the startup voltages. We try to answer this question. So let's review the three regions which we studied earlier. Let's review that once. So what happens when the three regions are cutoff, linear, and saturated? So the equations governing this is, if the gate voltage is less than Vt, the threshold voltage, the transistor will be in cutoff. If for both linear and saturated, the gate voltage should be greater than the threshold voltage. But if the voltage between drain and source is less than VGS minus VT, then it is in linear mode. If it is greater than, then it is in saturated mode. Do remember that the channel gets pinched off near the drain, and this pinch off is what causes the current to get saturated. The saturated current for an ideal case does not depend on VDS, but we saw that the actual transistor, the physical transistor, the current does increase a bit with VDS. The suffix N here just represents the NMOS. This is differentiated from the PMOS, which we will look into the other slide. So here the Vin is nothing but the VDSN, and VDSN is nothing but VI. Let's look at what the author has done here is he has converted the VGSN into Vin, so that the equations are now in terms of Vin and Vout. Why is that? Because Vin is common to both PMOS and NMOS. Similarly, Vout is common. Similarly, exactly same equation for PMOS, just the polarities become different. So VGSP should be greater than VTP. Again, similar equations. We again convert them into Vin. Now here the difference is that the gate voltage here at VSP is Vin minus VDD. This is just to make sure that the voltages values remain positive. So we have converted the VDSP to be Vout minus VDD and VGSP to be V minus VDD, since the threshold voltage of PMOS is negative. So these are the equations that are converted here. So since as I mentioned that VTP, since it's negative value, so Vin should be greater than VT plus VTP. This is you can put in this equation of VGSP here. So back we can put these equations back into this to get this equation corresponding with this equation and this equation. So this is just to make sure that the voltages are in positive range for analysis. We'll see how does that affect the graph. So these are the so on the axis, on the x-axis we have VDD, then the voltage which the maximum value is going to be. On the y-axis we plot the I. This is a typical IV curve. If you notice that if you take NMOS into isolation, this particular quadrant we have seen earlier. This quadrant we have seen earlier. This is the IV characteristic of a single transistor. It is not different than earlier. We saw that how this is the linear region and this is the saturated region, and we saw the dependence on VGS, that which increase in VGS, the IDSP increases. In saturated it becomes almost constant. Now since the voltages and currents are negative for PMOS, this quadrant here, this quadrant is for PMOS. If you take the mirror image, they are very similar figures. Now we saw earlier that the mobility of electrons being higher, the electrons move faster than the holes. So to make the inverter balanced, that means to make the PMOS carry the same amount of current as NMOS, we have to make beta n is equal to beta p, How do we do that? Beta is nothing but mu on C of W by L. Since mu n is greater than mu p, we make W of PMOS wider than the W of NMOS. So PMOS is wider, so that to make sure that beta n is equal to beta p and the currents are equal in both the directions. Now, what is done in this slide, and so what happened in this equation is that we are converting the PMOS voltages to positive value. What we are doing is that we are, in terms of graph, what we are doing is we are taking this quadrant here and overlapping it with this quadrant here. In other terms, we are solving equations by taking these values, this V in V out equations here, and the V in V out equation for NMOS, which is these. We are taking these NMOS and PMOS equations for V in and V out and plotting them on the graph, and the equation and the graph looks like this after conversion. This is a very interesting graph which shows how the NMOS current and PMOS current vary with input and output voltages, and what happens to V out. So this is the output voltage, this is the output current, IDSN is the NMOS current, absolute value of IDSP is plotted here. The PMOS current is represented in blue, the NMOS current is represented in green. Obviously, at any particular input voltage, IDSN should be equal to IDSP. So for a given V in, we plot. Now V out must be where currents are equal, because the currents have to be equal, since whatever is being drawn from VDD again has to go into ground. So the currents are equal, it satisfies KCL. So the V out, the output voltage, can be calculated from this graph at a point where the currents are equal. Now let's see the different points, the different voltages, and what happens to the current. Let's look at V in 0. Very clear. If V in is 0, let's go back to the compound graph, for example. So if V in is 0, this is V in 0 point, V in 0 voltage, V in 1 volt, V in 2, V in 3, V in 4, for example. So this is, in this direction the V in is increasing for PMOS, NMOS in this direction V in is increasing. So when V in is 0, the output voltage is VDD, the PMOS is turned on, the NMOS is turned off. So for this graph you don't see any green line, you only see the blue line, which is represented by PMOS. It's very clear. When V in is 0, V out is VDD. So this is the curve. What happens to the current? So the current, I'll come to that later. Let's first see the effect of voltage. Next, what happens when V in starts rising? When V in starts rising up to the point that it doesn't cross the VP of NMOS, the NMOS will still be turned off, it will be cut off, and PMOS, again PMOS is the one which is driving. So VDD is again, V out is again VDD, obviously on this line, and the transistor, we'll see what stays the PMOS in and what stays the NMOS in. But one thing is clear, that since the voltage does not cross V2, the NMOS does not start conducting. There is a very faint green line here which we won't see in this graph. We will see that in the next one. What happens when V in is 0.4 VDD? Now the NMOS has started turning on. The NMOS has started turning on. the PMOS is in some region, the linear saturation, we see that, and the two curves intersect here. So V out will be now slightly less than VD. Now see, V in is increasing from 0 to VDD. V out will start falling, which is the inverter functionality. Again, we see that whenever V in is 0.6 VDD. Now we see that the V in is more closer to VDD than it was closer to VSS. So now the NMOS is turned on. PMOS is kind of going into turn off. So we'll see V out, which is very close to V. Right. So V out, again we remember, is the point where both the curves intersect. So in case of if somebody is confused what happens when, so in this graph the IDSN is actually 0 flat along the x-axis. So this is the red point represents the intersection of VDD. So we again view this V in 0, the VDD is 0, the IDSP graph is represented by the blue line. V in starts increasing, VDD starts decreasing, NMOS starts turning on, PMOS starts turning off, and at V in is equal to 0.8 VDD and higher, the blue line is now along the x-axis because the PMOS is almost turned off completely, and NMOS is the one driving the out. So V in, so for V in 4, VDD is nothing but 0. The same thing happens if the process completes when V in is equal to V. When V in is equal to VDD, again IDSN represents IDSN is this curve, and VDD and V out is 0 for V in is equal to VDD. Now let's look at so this is again the same graph, the load line summary. So at any point of V in, either you could use the equation or you could use the graph. The equation is for more accurate analysis if you want to know the current value at each and every point. The graph is more intuitive into understanding that what happens during the switching of inverter. Now earlier the plots were IV curves, which means it was showing the current with respect to voltage. Now what we plot here is V in versus V out. If V in increases, what happens to V out? So all the points what we described earlier, 0, 0.2 VDD, 0.4 VDD, 0.6 VDD, 0.8 VDD and VDD are plotted on the input line, and we see V out here. So now 5 regions are defined: A, B, C, D and E. So this is a typical inverter functionality. Assuming this region here is very narrow, around VDD by 2. On the left of this region, V in is logic level 1 or VDD, and V in is 0, and V out is logic level 1 or VDD. And on the right of this point, V in is VDD and V out is 0, which is the red line. Typical inverter functionality. Now let's revisit the regions. So in region A, V in is 0 or close to 0. What happens to NMOS and PMOS? The NMOS is in cutoff, PMOS is in linear. So very important thing to remember is that in static state, whenever pull down or the NMOS is in cutoff, the PMOS, corresponding PMOS will be in linear region A. Region E, the reverse, PMOS is in cutoff, is in linear NMOS. So either NMOS or PMOS during the switching will go from cutoff to saturation to linear. Why this happens? Now the drain voltage is constant here. What is changing is the gate voltage, the input voltage. So when input voltage or the gate voltage is low, the drain voltage being higher pushes the transistor into saturation, and when the gate input keeps increasing, VDS, since the transistor comes out of the pinch off region and goes into linear. The thing to remember here is that at the logic levels of gain being 0 and 1, either the PMOS or NMOS, one of them is in linear, other one is into cutoff. Okay. Now what we will do is we will play on this curve. We will play on this curve. We will see how this curve is useful in understanding the noise margin and understanding the delay and so on. Now this curve can be skewed by playing with the beta p versus beta n value. If it is not equal to 1, now in the previous slide we saw that the switching point is very close to VDD. This is the switching point, and this the voltage shift in voltage is almost instantaneously here. This is for the case where beta n is equal to beta p. That means we have made CMOS wider compared to NMOS to make the current equal. But if this is not the case, this curve, the middle curve, is for beta 1. If we start increasing beta p by beta n, that means we start making PMOS wider, then this gate becomes skewed in the sense that the cutoff point starts moving away from VDD by 2. If beta p, if the PMOS is wider, then Vout, obviously Vout, it will be difficult to, it will take more time into, or rather it will take more voltage to convert PMOS into from a region of fully on or in linear to saturation to cutoff. So let's consider this curve here. Now this is the case at beta p by beta n is 10. That means PMOS is very is compared to NMOS is quite wide. It's 10 times as wide. So the PMOS will remain for a higher let's take it down there. For a major part of the beam to VDD ratio, the PMOS will remain in linear region, that is on, and NMOS will remain in cutoff for this major part of the curve. For the minor part, obviously the NMOS will be on. Similarly, this is the case. Similarly, this is the case where NMOS is it is again 10 times as wider as PMOS, and so this case is the reverse of this case, where for the major part of the curve, this is the major part of the curve, the NMOS will be turned on and PMOS will be turned off. So we see that by playing with the beta values or the width of the transistor, we can control the time it takes. So let's see this. We will look into the time factor later, but we can control the skew, the slew of this curve, and these gates which are not balanced, that is for beta and for beta, let's say this curve, this part of the curve, this kind of gate is not a balanced gate. It's called a skewed gate. How do we analyze other gates, other complex gates? We do the similar kind of exercises, and these gates also get collapsed into an equivalent inverter. So when we talk about the skew factor in terms of other gates, or how wide the NMOS and PMOS should be, we always compare it with an equivalent unit inverter. And I'll come to what unit inverter is later. We discussed some things about unit inverter earlier, but we will see that again. Now let's talk about noise margins. Noise margin, why is it important? For any gate, we have to make sure that a small amount of noise should not corrupt the value at the output of the gate. Now let's study two inverters that are connected back to back. So let's say the inverter, the first inverter. So the ideal voltages are VDD and GND. These are the ideal voltage, VDD and GND. Now let's say the output of the first inverter voltage here is, let's say, slightly lower than VDD. We call this as VOH. In case the value here is low, market level low, then it's not actually GND, it's somewhere higher than GND, let's call it VOH. What it means is that we are introducing some noise here, which is eating into the logic level. If the, let's say, if the input here, let's say, it goes high, the output here goes low, but it doesn't go low as low as GND, it goes only till VOH. If the input here goes low, then the output doesn't necessarily go to VDD, it goes to somewhere VOH. Now let's say we define two more terms called VIH and VIL. What it means is that the inverter here, for this inverter to recognize, for this inverter, this second inverter to recognize this value as 1, it is sufficient that it should be between VIH and VDD. I'll explain that in detail. I'll explain more in detail, but let's assume that this inverter, if given a voltage between VIH and VDD, it is able to resolve as logic level 1. Similarly, if we give a voltage between VIL and GND, it is able to recognize this as logic level 0. So we say that the logical high input range of this inverter is this one, is this wide. Similarly, logical low input range is this one. So for the second inverter, the noise margin, the margin it has, the lowest the input can go is VIH, but actually it is going up to VOH. So the margin it still has for high region is NMH, which is the difference between VOH and VIH. Similarly, the margin on the lower end is NML, which is the difference between VOL and VIL. Now let's look at logical high input range. In the previous slide, we saw this curve. Now consider an input value, the Vin, to be somewhere here, right? Now we see that for this range, let's say till point VDD to B, for this range of Vin, that means Vin can be higher than 0, and still the inverter will produce an output of Vin. This is called the range. That means the inverter is able to take some noise into account. Now inverter is a digital circuit. It operates in either 0 and 1. But the 0 does not mean it always has to be VDD. It always has to be GND. It can be some voltage above GND, and still the inverter will recognize this as logic level 0. Same thing happens for logic level 1. This range decides the logical high input range and logical low input range. Okay, now the gates should obviously be designed to withstand large levels of noise. So how to maximize noise margin? Let's say, for example, in this case, beta P is greater than beta N, greater than 1. This is to balance the inverter. And the curve slopes here. These are the 2 points. These are the 2 points where the curve, the slope is -1. That is, it's 135 degree slope is there on this curve, on this tangent. We draw a tangent, and we define these parameters here. VOH is this, and this is VIL. Again, VOL. So remember, the x-axis is the input voltage, the y-axis is output voltage. So what we are defining here is that we say that at these slope points, the output changes from VDD and immediately goes into a very sharp region. This is a very sharp transient region. So we don't want to go into this. We want to restrict ourselves to this particular region. To this particular region for input voltage 0. The voltage here we define as VOH, corresponding input voltage. This is the output voltage corresponding to this slope. This is the output voltage. This is the input voltage. So we call this VOH and VIL. Obviously, when O high because this is closer to VDD, I low because the input is closer to this. So for this input range, this is the VIL. Similarly, we have a similar slope here. This is VOL and VIH. So at these two slope points, if we design the inverter, these level logic levels for a unity gain point, it will have the maximum noise margin possible. Again, why is noise margin important? Noise margin is important to make sure that small disturbances in voltages don't cause wrong logic levels. I request all of you to go through this curve. Actually, the best thing would be to make a unity gain inverter, plot the DC transfer characteristics of a inverter which has beta p adjusted so that it's equal to beta n, or not beta n, actually twice of that, or let's say 1.7 times of that, to make sure the currents are equal. You draw this graph. This graph is very easy to draw, easy to plot. You just give V in and change V in and calculate V out. The Spice will do that for you. And then you could actually calculate the values of VOH and VOL, VIL and VIH. And that would give much more insight into the working of the inverter and the noise margin. So DC analysis told us what happens to V out if V in is constant. The transient analysis is very important. That will tell us what happens when V in changes, how fast or how slow does V out change. Go back to the RC circuits. The RC or the RL circuit is nothing but a first order differential equation. Similarly, we would have a differential equation here. Input is usually considered to be a step or a ramp. A step input is ideal case. A ramp input is the more practical case, from 0 to VDD or vice versa. So let's see this inverter here. Now it's important to we look at IDSN. V out will see some load, which will be represented by P load, capacitor load. This load is just the drain cap of both, or it could also represent the fan out load of, let's say, an inverter or any gate. So that we saw this earlier during RC model, but whatever load is on V out is represented by C load. So V in, we are looking to find the step response. When we talk about step response, V in will change from V in can be represented by UT minus T0 VDD. U is nothing but the step response input. That means U will rise, V in will rise at T0. It will become 1. Before time is equal to T0, it will remain at 0. V out, T is less than T0. If V in is 0, V out will be 1 or VDD. dV out by dt, let's look at the equation. So dV out by dt is nothing but is negative of IDSN by load, by C load. So the formula is simply I is equal to C dV by dt. So we solve for ID. So what happens when T is less than T0? We look for 3 regions here. T is less than T0, V out is greater than VDD minus V2, and V out is less than VDD minus V2. So for T is less than T0, obviously V out is VDD. It's connected to the pull up network, not to pull down network. So the current through NMOS would be 0. Again, we look at these 3. Now V out is nothing but VD. We look at 3 regions here. V out and input is nothing but VDD. It's a gate voltage. Just so this is nothing but this is VD, this is VG. So if VD is greater than VG minus VT, we can write. So this part is nothing but this is VG, and this part is nothing but VD. Just rearranged. So VD is greater than VG minus VT. It's in saturation. You remember the saturation equation. Again, this is into linear region. This part we remember the equation of the linear part. This is solving for, this is the ID values. Now we have to solve for V out. Knowing the ID values, we could easily plug in the value of IDSN here and calculate the V out. This graph here shows what happens to V out when V in changes suddenly. Obviously, V out will go to 0 after some time. Since the pull down network is being active now, but we are looking to find the equation for this curve. So here we will define some parameters for delay. TPD means propagation delay, R means rise, F means fall. TR means how much time it takes this for signal to rise. TF means how much time it takes for the signal to fall. TPDR, rising propagation delay, that means from input to output rising crossing VDD by 2. The rise here, the rising here is referring to the rising output. For any gate, this can be for any gate. So for an inverter, a rising output would mean a falling input. For let's say a buffer, a rising output would mean a rising input. So PDR is rising propagation delay from input to rising output. TPDF is falling propagation delay from input to falling output. TPD is nothing but average of both. TR is from output crossing 0.2 VDD to 0.8 VDD. This is the transition time for the output. This is a 20-80% limit. So 0.2 VDD to 0.8 VDD. Again, fall time is from 0.8 VDD to 0.2 VDD. These things are arbitrary. For a particular technology, for a particular design, somebody might decide to use the 10-90%, so 0.1 to 0.9, and so on. So these are just definitions for, let's say, for one particular technology, for one particular application. These can be changed as the purpose is. Now TCDR is rising contamination delay from input to rising output causing VDD by 2. TCDF is the falling contamination delay. I'll come to what is this contamination delay. This contamination delay, for example, is not applicable for inverters. It's only applicable for complex cases. So this is a SPICE simulation of an inverter. I would recommend all of you to do this yourself using the SPICE tool. Obviously, SPICE will not use your simple Shockley first order model or a simple alpha model. It will use a much more complex and accurate IV model. Obviously, simulations are not that easy to write, but once you are familiar with, you can write basic simulation. At least you can simulate a step response, or you can even simulate a step response in steps of 20% of VDD. You can do that easily. So this is a graph of a SPICE simulation where the time is plotted here. So we see the curve here. This V in is rising. This is nothing but V in, and so obviously when V in is low, this part when V in is low, VDD is high. When V is high, the VDD is low. So according to the definition of the propagation delay, the time here and the time here, the difference in time is the propagation delay for fall. That means V out is falling. Similarly, this is the propagation delay when V out is rising. I'll also show you what is the rise time and the fall time. So the propagation delay refers to the difference in time between the output and the input when output is falling or output is rising. If you consider the VDD alone, so the time it takes from this point, let's say 20% of VDD, to go to this point, let's say 80% of VDD, this difference here, this is nothing but the rise time. Similarly, This difference here is the fault length. So these two, I request you all to again go through this, to revise this such that these concepts are very clear of the propagation delay and the rise and fall time. These are very important factors in determining the quality of a gate, quality of a design. Now we realize that solving equations or doing spice every time is not a straightforward thing. It's not very easy for every gate. So how do we quickly compare different designs for delay? We saw one thing earlier. We saw an RC delay model earlier, which is used to estimate delay on paper. It's a very good tool. So the point here says that we use RC delay models to estimate delay. It's a very useful technique. Propagation delay is proportional to RC. We also characterize transistors by finding their effective R. So the effective R depends on the average current that the gate pushes. Let's look at RC delay model again. So we talked about a unit NMOS transistor and unit PMOS transistor. We say that the rule of thumb says that if a unit PMOS has a resistance of 2R, then the mobility of holes is slower compared to electrons. Capacitance is same. We define the capacitance to be C of each gate, drain, and source. The capacitance is proportional to width. We represent width by K. The resistance is inversely proportional to width. So an NMOS of width K will look like something like this. You have capacitance Kc at each of the 3 terminals, and you have the on resistance to be R by K. Similarly, PMOS will become 2R by K, with the capacitance will remain Kc. Let's again give an example of this. Let's see a 3-input NAND, and how do we make sure that it achieves the effective rise and fall resistance equal to unit inverter R. So now what I would do is let's look at the RC model of a 3-input NAND and try to see how does it compare to a unit inverter. Now first thing what we have to do is we have to assign width to all these NMOS and PMOSs. Now how do we do that? I'll annotate some numbers here. I'll try to justify these numbers. I'll justify these numbers by the width is written as 333 and 222. And then this technique can be applied to any CMOS, a static CMOS gate, and widths can be calculated. So let's see a unit inverter. So a unit inverter, nothing but a PMOS and an NMOS connected in series. So this is a PMOS here, this is an NMOS here, they are connected here. So the width is 2 and 1. So if you remember that this unit NMOS here will have the resistance of R. The unit PMOS here will also have a resistance of R. Why? Because the width is 2. So if it's 1 here, the resistance will be 2R. If it's 2 here, the resistance will be R. This, we go back to the previous slide. We see that the if the width is 1, so NMOS will have R by 2, and if width is for corresponding same PMOS, it will have a 2R. So by making the PMOS to be twice as wide, we keep the resistance to be R. Same thing we'll apply here. Now if you see, let's say if you combine 3 NMOS in series, these are 3 NMOS in series. Forget the number 3 here, forget the width. If let's say each of them was unit, so the resistance, total resistance would be 3R. Now if we make each of these transistors wider, 3 times wider, what happens to the resistance? So the resistance of each of these becomes R by 3, which is R by 3, R by 3, R by 3. So the total resistance seen by the pull down is nothing but R. So now compare the resistance by a pull down circuit here is R, resistance of a unit inverter is R. Now we come back here, these are parallel, PMOS is in parallel, but this is a NAND gate. At any given time we assume that only one PMOS would be on, other two PMOS would be off. It's parallel, so we assume that only one is on at one time. If one is on, the resistance of a PMOS is single PMOS resistance on resistance, which is equivalent to the single PMOS resistance of an inverter. So it should also be R. So PMOS is nothing but twice as wide. Now what I would request is that go back and draw a 3-input NOR gate, for example, or any gate, and try to calculate the widths of NMOS and PMOS using the same logic and comparing it with a unit delay inverter. I repeat again the process. You go to the pull down, and the total pull down resistance should be R. If it's in series, the resistances add up, and you will have to make the NMOS as wider to make it R. Then go to the pull up and compare the pull up to the unit resistance pull up. If it is in parallel, you assume that only one of the PMOS would be active and calculate the width. So for series, you will have to make the transistor wider. For parallel, you might have to make it less wide, or depending on how the parallel circuit looks like. So do this for one complex gate and compare the widths. Now we saw the widths of all the PMOS and NMOS. Now let's annotate the capacitance and resistance over it. Right? We'll convert this to. This looks very complex, but not that in reality. Just so a width of 3V means 3C at each of the gate inputs, 3C cap at each of the gate inputs, 3C cap at each drain and each source. Right. Then again this the PMOS is 2C, so this gate cap. Now see, for NMOS the cap will be with respect to ground, for PMOS the cap will be with respect to VDD. So 2C, 2C, again 2C, these are parallel connections. Please note these are parallel connections. So 2C, 2C, each will have a 2C cap with respect to VDD. Now let's check out one thing. 2C here, the gate, 2C, 2C, yeah, 2C, 2C, yeah, okay. Now, if we are wondering, this is 3C. This is just because it shares the contact. So because it's not contacted, so we account only 3C for one of the transistors because it shares the diffusion region. There's no contact here, as we saw on the layout. Now we combine this. What we do is we use the so for example the 2C, this 3C and this 2C is combined to make it a 5C, because see, VDD, then 2C, then 3C. This 2C and 3C are in parallel. They'll add up to become 5C. So each gate will see 5C, and similarly we combine the drain and source one wherever it can be combined. So each gate will see 5C. Let's go back and check the output. So the output here, this point sees a 3C, 3 plus 2 7 plus 2, yeah, sorry, 3 plus 2 5 plus 2 7 plus 2 9. So the output will see 9C, right? Similarly, this point will see 3C, this point will see 3C, and so on. Now let's see the delay part. So we have the value of R, we have the value of C. Now this is again an exercise into sizing. So So before calculating the delay, the first thing we should do is determine the width of the transistors. Second thing, we annotate these values there to calculate the capacitance seen by the output, because the delay at the output determines on the output capacitance and resistance, right? So this exercise, we'll try to size this so that this becomes equivalent to a unit inverter, right? Now here D is in parallel, so these two are parallel connections. So we make sure that D has the same R as the NMOS of a unit inverter. So that means the width here will be 1. For example, if the width here is 1, then again these two are in series, so they will be twice as wide. So I'll put the values here and we justify. So the width of D is 1. Next, this should be 2 and this should be combined. This should see combined. This sees by width 1 means this sees R. This should see R by 2 and this here should see R by 2. So the width here is 2. Again you have parallelism. So B and C would need to be still more wider to draw the same current. I'll just clean it up a bit. Yeah, okay. So since this part is parallel, yeah. So this D is parallel to this circuit. We assume only one of them will switch on. So each one of the branches should have resistance R. So that's why the width is 1. Again, this part in total should be, again B and C are parallel. So we assume that either of them will be turned on. So when A to B is turned on, you see 2 and 2, that is R by 2 plus R by 2, again R. Or if AC path is turned on, you see R by 2 and R by 2, again R. So 1, 2, 2 and 2. Similarly for pull up, we see that D is in series. Now to A, B and C, again I'll put in the numbers here. So when D is in series, let's put the numbers. Let's start from A, B and C. Yeah. When BC in series, now usually the PMOS is twice as wide. Now we'll assume that either, let's say this will work. This part will be active. Either this will be active or this will be active. Let's label it 1 and let's label it 2. So when 1 is active, D and A being in series, PMOS anyway shows a 2R. Usually it's too wide, it's twice as wide. If you add one more PMOS, it should be 4 times as wide, so that the resistance shown here will be 2R by, this is 2R, nothing but 2R by 4. This is A is 2R by 4, D is also 2R by 4 or R by 2. When you combine 2R by 2 together, it shows R. Again B and C here in series, so this should be again twice as wide as A. So the resistance here is again 2R by 8, so R by 4 and R by 4 plus R by 2. So this becomes R. So this way we decide the widths of each of the transistors. I request all of you to do this exercise on paper on yourself, or you can draw any complex circuit and try and do the sizing. The purpose of this sizing is to make sure that the resistance of the pull down and the pull up network is same, and it is equivalent to a unit inverter. Right, now we define a term called Elmore delay. Elmore delay assumes that on transistors looks like resistors. The pull up and pull down network are modeled as RC ladder, what we have been doing, and the Elmore delay of RC ladder is the propagation delay is, let's say you have a network like this, the summation of Ri to source and Ci across all the nodes. So the delay here would be R1 C1 plus R1 plus R2 C2 plus R1 plus R2 plus C3 into C3. So this is a formula proposed by Elmore, which is called Elmore delay, to give a very quick calculation of a delay. The delay, the numbers will not be accurate, but using this you can compare two designs. That analysis would be accurate at least. The absolute value of delay doesn't matter. So the PD, that's why we say that propagation delays can be represented by this formula. This is a very popular formula to compare multiple designs. For example, 2-input NAND. Again, take pen and paper and see that the widths here are actually correct according to your understanding, and the values here are correct according to the RC model. I am not going to go into details of the width, the calculation of width of a 2-input NAND, or into the how the values of C are calculated here. This everybody should be able to do this exercise now. So we say that we try and calculate the delay, estimate the delay for a NAND gate driving H NAND gates, H identical gates. So I'll break it here. The part on the left is this NAND gate. The part on the right is this circuit. Since it's H and each gate input gives 4C, so the capacitance here is 4HC. 6C, 2C. We saw how this calculation we calculated earlier. So now we try and calculate. So now when one of the PMOS is on, okay, let's say when the output is rising, when will output rise? When will the NAND gate have a 1 input? When any of the input is 0. So we assume only one of the PMOS is active, and it connects to pull-up network. Pull-down network is not shown here, right? So this part kind of goes away. This part kind of goes away. So the capacitance left is 4HC plus 16, and the resistance on R here. So TPDR according to Elmore delay will be nothing but R into 6 plus 4HC. Right. Now let's look at the fault delay. In case of fault delay, the circuit will be seen is only the pull down part. So again 6 plus 4HC, and we'll see a 2C, this 2C at the gate, and this 2C. So this part is this part, and then from Y it goes to A, from Y it goes to A, R by 2 and 2C. This one is 2C, and again to B, which is nothing but R by 2. So TPDF, the Elmore delay will be, so Elmore delay will be R by 2 into 6 plus 4HC plus R by 2 into 2C. So it will be 7 plus 4HC RC. This might seem complex at first, but if you go back to the Elmore delay formula and apply it here, it's a very simple network. So this R by 2 into 2C, then this R by 2 plus this R by 2 into this part. So the TPDF is 7 plus 4H into RC. This is how we estimate. So first we do the sizing. Second, we annotate the value of capacitance onto each of the inputs, the gates, the source, and the drain. Then to calculate the propagation delay in either the right side or the fault side, we first analyze which part is active, either pull up or pull down, and then we take only the relevant part and then apply the Elmore formula to estimate the delay. Right. Now the delay has two parts. We saw earlier either this 6RC, that means the one at the left of it, another at the right of it. So one is the parasitic delay, that means the delay which is independent of load. We saw that a NAND gate driving H identical gates, at one level it sees a cap which is inherent to its gate design, which is called the parasitic delay. We saw it is either 6RC or 7RC. This is independent of load. Other is the effort delay, which is nothing but the effort the gate requires to drive the fan out. It depends on the load, proportional to load capacitance. We saw it's always 4HRC. It would be this doesn't matter when output is rising or falling. It just depends on the gate capacitance of the fan out gates, of the connected gates. The contamination delay, now we have been assuming all along during the delay calculation that only, for example, for a 2-input NAND gate, only one of the input will fall at one time. Either A will fall and B will remain constant, or B will fall and A will remain constant. The contamination delay refers to the condition where both the inputs are falling simultaneously, and this can be much lower than substantially lower than the regular propagation delay, which means that the input will shoot to output quite fast compared to the other two cases. So for calculation of contamination delay, again since we are assuming that both A and B are falling, so we have to assume that we say that both of these are active. Now see, we have determined the widths 2, 2 and 2 and 2 of PMOS and NMOS, assuming that only one of the input will transition at one time. We did not assume a contamination case. Assuming the widths to be same, we calculate the contamination delay. So the contamination delay is 3 plus 2 HRC. Please work this formula out, and it should be easy to calculate. I will not go into details again. Now this contamination delay is usually whenever the timing is calculated for the standard cells while preparing the library, this contamination delay is usually not taken into picture. Why? Is because the probability of all the inputs of a multi input gate falling together is very low, but we know this to be a dangerous case and we tackle this in other ways, but we do not take into account the delay part. We are only interested in the delay whenever only one of the input is falling. How do we tackle it during digital design is a separate topic altogether. How do we tackle contamination delay? I am not sure this is in scope of this course, but there might be a mention of it when we do synthesis and timing analysis. Just keep this in mind that contamination delay is one unwanted factor, and usually the delay part is not part of our calculation. Okay. We assume contacted this slide we discussed earlier, that wherever possible a good layout will minimize the diffusion area. For example, we saw the NAND 3 layout that the region where it says merge in contact is diffusion. We see that since the NAND since this part here shares it doesn't need a contact, since it doesn't need a connection outside, so we don't put a contact here, we share the diffusion area. And that is why we say that this NMOS here and then at this NMOS here, ideally if there was a contact here and if they don't share the diffusion area, this would see 3C, this would see 3C, this would total will be 6C, but we only say 3C here because they share the diffusion area. So we are assuming that good layout practices will be followed and the diffusion will be shared and there will not be any contact. So this will reduce the output capacitance also. So that is why good layout practices are mandatory. So this is one example that which layout is better. I will leave it up to you to analyze which layout is better. I'll tell you the answer. The answer is part A. Please go and figure out why do I say that A is better than B, or the left side is better than the right side, based on whatever we have discussed in the earlier slide. So this chapter was, I agree, this chapter was a bit more complex than the earlier chapter, but it sets the tone for the coming chapter, where we know now that the first chapter concentrated on how do we design, how do we stitch and put together different PMOS and NMOS to make a complex gate. This chapter concentrated on how do we decide how wide the transistor should be, and plus when we've already decided how wide the transistor should be, how do we calculate the resistance and capacitance, how do we annotate those values, how do we calculate the Elmore delay. Again, please note that Elmore delay is a very approximate way of calculation. I will not recommend using Elmore delay in actual scenarios. It should only be used when you want to compare two different surface styles. For example, here when you want to compare the layout on the left and the layout on the right, you could actually annotate capacitance and calculate Elmore delay and decide which of the designs is better. So Elmore delay is usually used to compare different design techniques, not in the actual value of the delay is not taken. Right? Please review the width part, where we decide the width of the NMOS and the PMOS transistor carefully. take the circuits such as the assignment is take the circuits such as 3-input NAND gate, AOI to let's say 2-input NOR gate. Define the sizes, annotate the R and the C values, and calculate the rise and fall propagation delay based on the Elmore formula. This is the assignment for this chapter. Thank you all.